Okay, so in the last video we talked about average velocity. In this video we're going to define instantaneous velocity. Okay, so average velocity was displacement over time. Instantaneous velocity is basically going to take the limit of that, right? The limit of displacement over time, or the limit when delta time goes to zero, right? So the idea here is that as we make that time interval smaller and smaller and smaller, we approach the actual velocity at one given moment. Right? And we'll note that anytime you're taking a limit like this is basically our definition of a derivative. So to calculate an instantaneous velocity, we can use calculus. So the derivative of our position as a function of time is going to give us the velocity, the instantaneous velocity. So more graphically, we have some position versus time graph here. Right? And the blue line represents our position as a function of time. So at time equals 0, I'm close to x equals 0. From time equals 0 to time equals 1 second, I'm not moving very fast. I move a very small distance in that period of time, so I'm obviously moving somewhat slowly during that time period. Where I can see from time equals 4 to time equals 5, I'm moving from here to here. So I'm moving a much further distance in the same amount of time. So I can tell that as time is moving on here, I'm moving faster and faster and faster. Right? This blue line is getting steeper and steeper and steeper. The slope is increasing and increasing and increasing. So that's telling me I'm going further in the same amount of time, and I must be going faster and faster and faster. Okay. But I can also pick any 2 points, so I could pick point 1 and point 2, so from time equals 1 to time equals 3 seconds, and I can measure my average velocity during that time period. Right? During that time period, I moved this distance, delta x, so I can read it off this axis over here, and I move 150 meters, and I did that in some amount of time. I did that in 2 seconds, which is this distance here. So calculating my average velocity of displacement over time, my average velocity during this time period was 75 meters per second. Okay. Now let's see what happens. I can make my time interval smaller. Instead of 2 seconds, I can make it 1 second. Right? So in this case, I could also calculate my average velocity during this time period. Right? And now the question is, what happens when I make this time difference basically infinitely small? Right? If I take the limit with delta t goes to 0, this line drawn between these 2 points basically becomes a tangent line. Right? So that's what a derivative is. Right? It's telling us the slope at a given point. Okay, and so that's how we're going to calculate instantaneous velocity. Instead of drawing a line between 2 points and finding the slope of that line, we're going to draw a tangent line at a given point and figure out the slope of that tangent line. Right, and that is what our instantaneous velocity is. That's our velocity at one given moment, and that's exactly what a derivative is. Okay. And there's a few ways to think about velocity, a few ways to picture it. I could draw what's called a motion graph, which is just pick like 5 different moments in time and draw a position graph at that moment, meaning this is just my number line where I have my origin, and this is the plus x direction. So I can say at this initial time, time A, I'm located at this spot, some negative position, and I have some positive velocity. All right, I'm moving in the plus x direction. At some later time, time B, I am now located at the origin, and I still have some positive velocity. In fact, my positive velocity has an even larger magnitude than it did before, right? Because this vector is bigger than over here. At some later time, time C, I now have 0 velocity. I'm at this positive location in x, but I'm stopped momentarily. At time D, I now have a negative velocity, right? So I have some positive position. I'm at this location, so I'm to the right of the origin. I have some positive position, but I have negative velocity. I'm moving in the minus x direction. And some later time, time E, I still have some positive position. I still have some negative velocity, but my negative velocity has a smaller magnitude than it did before. Right? This arrow is smaller. And we could also try to graph exactly this motion on a position versus time graph. All right, so initially I have a negative position, so at time equals 0, right? I'm to the left of my origin here. That means I have some negative x value. So I can graph that. At that moment I draw that black dot, right, for I have a negative position. At some later time, time B, I'm at the origin, right? So at time B, I just say I'm at the origin. At some later time, time C, I am at some positive position, some large positive position, so I'm right here at some large positive position. At some later time, I still have a positive position, but it's not as large, so I'm at point D. And at point E, time E, time has progressed some amount, I still have some positive position, but I'm right here. But I can also think about how does velocity behave, right? So at time equals 0, I'm again at position A here. I'm at this negative position. But I also know that I have some positive velocity at that moment. That tells me that the slope of the tangent line at that point has to be positive, right? So this green line is my tangent line drawn at this point. So where this blue line is my actual path, or my actual graph of my position as a function of time. Right? So I know at this moment I must have some positive slope because I have positive velocity. Right? At time B, I have much larger positive velocity, so that tells me that at point B, I must have a much larger slope to my tangent line. Right? So at both A and B, I have positive slope to my tangent line, but at point B, it's more positive. Right? It's a steeper slope corresponding to a steeper velocity, a larger magnitude velocity. At point C, I have 0 velocity, and we have to note that in our position versus time graph, as I have 0 slope at that moment. Right? At that moment, my tangent line is completely horizontal, corresponding to 0 slope. At point D, I have negative velocity. That means I must have some negative slope on my position versus time graph. And at point E, I have also negative velocity, which means I have to have some negative slope. But I'll note that at point E, it's a less negative slope than at point D, right? Because this is a smaller velocity. So these graphs can really help you in understanding this type of motion, and even if a problem doesn't ask you to draw these, they can really help you picture what's going on and help you to solve the problem. So let's go back to our example from before. We've seen this position versus time graph already of this person walking, and I've zoomed in a little bit, but it's the same graph we saw earlier. And I can pick different moments in time, for example, from about time equals 7.5 seconds to time equals about 9.5 seconds. So during this time period, I can calculate the slope by looking at my changing my position in some period of time. And when I do that, I find the slope of this line is 4 meters per second. And then I can also graph that on my velocity versus time graph. I can graph a constant 4 meters per second, right? During this time period, I have constant slope. That tells me I have constant velocity. So during this time period, I have a constant velocity of 4 meters per second. Right? So we're very experienced with position versus time graphs. Now we're introducing the idea of a velocity versus time graph. It's also going to be very helpful to us in solving these problems. I can look at other parts of this motion, right? During this time period, from about time equals 4 seconds to time equals 7.5 seconds or so. During that time period, my position versus time graph is 0 slope, so it tells me I'm moving at 0 meters per second, right? I'm at rest during this time period. So on my velocity versus time graph, I just need to graph a constant 0 value during that time period, right? So whatever my slope is here, I graph that value here. So my slope is 0, I graph the value 0 here, right? I'll note that my value here on this graph is not 0, right? I'm at about x equals minus 4 or so during that time period. But my slope is 0, so my velocity is 0. During this time period, right, I have negative slope. In fact, you can calculate it's about negative 3 meters per second. So I would plot on my velocity versus time graph a constant negative 3 meters per second of velocity, right? Because I have negative slope here, that corresponds to a negative velocity. It's constant slope, so it's a constant velocity. All right, so we're going to get a lot more experience with interpreting and drawing these motion graphs. Okay, and one quick note. We've talked about how we can, from a position versus time graph, we can calculate velocity just by at any moment we can draw a tangent line, and we can figure out the slope of that tangent line. So if I was to just give you this blue line on this position versus time graph, and I give you some numbers on this graph, you should be able to draw in a tangent line at any given point. I could pick any point on this line, you can draw a tangent line, and from that tangent line you can figure out the slope. And once you know the slope, you have a measure of the instantaneous velocity at that given moment. Okay, but there's another type of problem you can get where I could tell you the position as a function of time using an equation, and you could use our definition of velocity to solve that. Right, so I could tell you the position as a function of time is equal to this equation. It's equal to 5 meters per second cubed times time cubed minus 3 meters per second squared times time squared plus 9 meters. All right, so this is a position as a function of time, and you could use this to tell me my position at any moment. You just plug in any time to this equation, and it tells you your position. Right, so for example, at time equals 0 seconds, you plug in 0 here, and that tells me my position at time equals 0 seconds is x equals 9 meters, right? Because that's the only non-zero term. Where at time equals 1 second, I plug in 1 here, so this is 5 meters per second cubed times 1 second cubed, so this ends up being 5 meters. This is minus 3 meters, and then plus 9 meters. So I end up with, at time equals 1 second, my position is x equals 11 meters, right? So this tells me my position at any given time. I can now use this equation, right? Velocity is just a derivative of position as a function of time, to figure out my velocity at any moment in time. I just take a derivative of this entire formula, right? So 5 times t cubed, the 3 comes down to become 15t squared, minus 3 times t squared, the 2 comes down to becomes minus 6 times t, and then my constant term goes away when I take that derivative. So now I have an equation that tells me exactly my velocity, my instantaneous velocity at any given moment. Right? I could plug into this equation time equals 0 seconds. This is 0, so my velocity at time equals 0 must be 0. Right? I could plug in another time. I could plug in time equals 1 second. This ends up being 15 times 1 squared minus 6 times 1, or 15 minus 6, which is 9 meters per second. So my velocity at time equals 1 second is 9 meters per second. Right, so this is another type of problem you'll see often in this chapter.